Let us continue our discussion with other matrix vector derivatives or vector matrix derivatives. So as we can see here, we want to find the derivative of the elements of W or with respect to the W for the function Y. Well, that's the function of X. So you can consider this as f of X. So we want to essentially find the dou F by dou Wij or Wji or dou F by dou W itself. Okay, this is the objective of us, right? So let me just, so essentially let us start with dou F by dou Wji. So here, as you can see, the vector Y is Y1 to Yn, and then W is this matrix, N cross D matrix, and X is D cross 1 vector. And Yk can be crisply written, any of the element of Y, Yk can be written as Wki into Xi, I varying from 1 to D. Right? So now dou Yk by dou Wki, if I find it is Xi. But if k k is the only particular row in this matrix W. So it say there are other elements of W with which also I would like to find the effect or the variation in the Yk. So if there is some variation for other elements in the matrix W, does they change any perturbation in Yk? So that if we see dou Y K by dou Wji, where J is not equal to K, it is equal to 0. So more specifically, this can be written now as follows. So dou Yk by dou Wji is equal to Xi if what? If J is equal to K, right? If these two are same, the numerator index and the denominator index, this index and the row in which I am finding the rate of change of that particular W in this row versus the element in this. If both are same, it is Xi. Okay, if both are same, it is Xi. However, if both are not same, it is 0. If J is not equal to K. So now how do I write this? This can be written in a crisp manner that dou Yk by dou Wji as delta J is equal to K or K equal to J into Xi, right? So Wj can take all values, but Yk is fixed, with which I want to find out the derivative. So if the J takes the value that is K equal to J or J equal to K, then it is 1, otherwise 0. Into Xi, the value when it is from J, Wj is from that kth row, then the derivative value is Xi. Fine. This is the element wise derivative, and this is finally a scalar. This scalar, because as you can see here, it's essentially even though there are 3 indexes here, it's finally a value that we are getting. So now let us see the other derivatives. So we want to find out the derivative with respect to the matrix elements for the whole vector Y now. Okay, so dou Y by dou W Ji. Fine, with respect to particular element only, but I want to find with respect to all. So what happens in that case? See, with respect to the first one, if I differentiate, it is say if J equal to 2. Okay, so then with the first Y1, if I see W21 won't be there, or W22, any of the W2 second row of W's will not have any impact on the variation of Y1. So it is essentially 0, right? So then the second row of W will have some effect on the Y2, and hence it is non-zero. And that effect is how much? Dou Y2 by dou Wji is anything but X I corresponding Xi, right? So essentially this same expression, same thing, the answer is same for all the combinations of I, J and K. However, dou Y by dou Wji, when we write, that combination we take where all K's are there and for a particular Ji we are given. So this can be written as a column matrix, column vector, or as a row vector, because y is a column vector, we can also write as a column vector. However, as we have seen for the definition that we have given here, if the vector is in denominator and the derivative when we are finding with respect to a vector, we have written as a column. When we are finding derivative for a vector, we are writing in row. Okay, so this is the notation we are following here. So given this dou y by dou xi, any particular index or any particular scalar for the vector y, even though if it is like this, we are writing it as 1 cross n vector. Okay, so sticking to this notation, what we write is, even though intuitively this is a column vector that we have to write, but given that this is the standard definition or the notation we are following, so let us write this as a row vector. That means this is actually a row vector where it's actually 1. Okay, this if I write this as 1, 1 or whatever, 1 row vector where k equal to z. So it's a row of k equal to z, and then xi is the wherever the derivative is non-zero, the value of derivative is xi. Okay, and then 1 or kz is nothing but 1 row vector. Okay, equal to z is nothing but 1 0 0 and so on, 1 wherever the k equal to z, here. Okay, so at k equal to z, otherwise it's 0. So this is how we represent, and the dimension of this we now write it as n cross 1. Please note that if y is n cross 1, this is also this is equal, this is 1 cross n, because we have written it as a row vector, right? So this, please note this, right? This is for the notational convenience, we have written like this. So now if you want to write dou y or dou yk by dou w, what we want to write here, we want to write actually a derivative of the particular yk, one of the element of the output function in the function, by the whole matrix. So this finally turns out to be a matrix output. So the derivative also will have a dimension same as w, that is n cross t. This also will be n cross t, right? And the answer now, if we write here, is how much? So dou w, so we can write in terms of xi. So because for each, it's essentially each element is, if just going by this again, whichever we have finally got here. So this is the guiding principle to write even this. So this becomes a matrix. Okay, and this matrix is nothing but so 0 0 0 0 everywhere, and when k equal to z, that particular, whenever we consider the corresponding k, if k equal to 2 here, so for that particular k it is non-zero, and the value of that non-zero is x1 to xt, right? So k equal to 2 means it is non-zero, and x1 to xt, because we sample corresponding xi from here as non-zero derivative, right? And then 0 elsewhere. Okay, that's what we get. So this essentially can be written in different ways, but let us try to write in terms of what we have defined earlier. So this can be written as 1 or, okay, 1 row k equal to z. So this is a row vector. So since this is row vector, so we can multiply with, this is actually 1 cross n. So we can multiply with, so transpose of this, let us take, okay, multiply with x. So this is now column vector, multiply with x transpose. So the x is a row vector. So we just made the arrangement such that we get this matrix. So this is actually a column vector. This is made as column vector, and this is made as row vector. So this multiplication will give us this one, right? This product will give us this. So this can also be represented as the x into this. So this we can write in a compact way, 1 k equal to z into x transpose. Okay, so we are just writing one, the column vector is conventional vector, so 1 k equal to z as column vector. Okay, so essentially yk dou yk by dou w, we are writing it as this. Now, if we write, no, the other thing to write is dou y by dou w. So what this will be? Dou y by dou w. This will be a tensor, because it will have three variables k, j, and I. Also, and this is the tensor dou yk by dou w and k equal to 1 to n. Right? It's a tensor. So we leave it here. So given these background, let us try to now understand and see how the vector backpropagation equations will look like in a feed-forward neural network. Now let us come back to the discussion we had. So in the previous class, we have seen this small network. This is a feed-forward network wherein there is only one input and output layer, no hidden layer. And the connections we can see are actually from hidden to out, input to output. So ith neuron here might have been connected to kth neuron here. Okay, something like that. So there is no hidden neuron that we have taken. Since there is no hidden neuron, even though there are connections from multiple input features to output neurons that happens. So the only summation of different weighted inputs is determining the output at a particular output neuron. And hence it is just a linear function of several inputs, weighted sum of inputs, and modulated by whatever nonlinear function f. But still, it's only a linear function, that is each of the O1 to OC, if we consider as output O1 to OC as output neurons, the outputs from the output neurons, then they're all proportional to linear functions, also are proportional to the net values, right? So since this is a linear transformation, this still this network is a linear classifier. This can only perform linear classification, or linearly separable samples only it will be able to classify. So to classify non-linearly separable samples, we may need to have a hidden layer. Okay, that we will discuss subsequently. So now let us discuss in this framework how to do vector backpropagation. Backpropagation in vector matrix formulations. Okay, so let's come back to this discussion a little later. And now let us review the expressions that we have got in the last class. So we have seen that actually the gradient descent is the principle with which weight update happens. We have written element-wise backpropagation like this. So dou lk by dou ok by dou net k, and dou net k by dou wj, where lk is the total loss at that neuron, and L is the total loss. LK is the output loss at that neuron, and OK is the output at that neuron. Net K is the net value before taking activation at that neuron. Okay, so we have seen this net value is related to the output by this net K is related to output by this expression. Okay, this is what we have seen in the last class. And OK is equal to f of net K. So this is essentially, even though f is a function applying on a vector to vector, it is a scalar function. So corresponding, it is just it's not a it is element to element mapping. Okay, so the net I is mapped only to OI. Okay, please note that. Also, this will be useful in writing the derivatives. These all relations which are interdependent from forward pass to output pass will be useful for understanding how to write the dependency of the derivative of this to the backwards. Okay, so now let us, given this, let us write now dou L by dou Wj. So here what we are writing? We are writing actually derivative of a scalar function L finally. Okay, this is a scalar function with respect to the vector element Wj, right? So this can written through chain rule in vector form as since L, as you can see, L is a function of L is a function of O minus T, okay, whole square in vector formulation. And then O is a function of net value, okay, by element mapping. And net is what? Net equal to W into X. These are the relations we had. Okay, so given these relations, so now we want to write the back propagation. So the back propagation, how does it happen? Dou L by dou O and dou O by dou net. Okay, and as you can see here, dou L by dou O and dou O by dou net and dou net by dou W. That's what we are exactly writing here. Okay, this is how the back propagation happens. While writing, we'll write like this. So now, given this dou L by dou O, what is dou L by dou O? Dou L by dou O is nothing but O minus T, which is very clear from here. Okay, and then dou O by dou net, both are vectors here. Since both are vectors, so this we need to see the dou L by dou net will be of what dimension? It will be a matrix. However, OK is related only to net K. And hence, if we see little carefully, dou O by dou net will become a diagonal matrix, because F dash essentially, since you see that OJ is related to F of net J, O2 is not related to net 1. Okay, so in that sense, whenever there is no dependency, the derivative is 0. So and hence all the cross diagonal elements will be 0, and dou O by dou net is nothing but F dash net 1, F dash net 2, and F dash net C only in the diagonal, right? And this we can represent as a diagonal matrix, a capital F dash. Now this is what we get as the derivative for dou O by dou net. Now dou net by dou Wj. As we have seen before, dou net by dou Wj is equal to, so one, we have seen actually, what did we see? This is a row vector. And then this one row, a row vector of ones, one like binary vector. So it will be 0, 0, 0. Only at k equal to z, it is 1, and 0 elsewhere. Okay, at k equal to z. Right? This is what we have seen before, and multiplied by xi. Because it picks dou net by dou Wj, picks the value of xi in the differentiation. Right? If j corresponds to the particular row of net I am looking at. Okay, so particular row of the numerator variable that we are looking at, right? And hence this will be equal to 1 into 1 row into xj. Fine, and this is a row vector. As you can see the dimensions here, this is C cross T, this is C cross C, and this is C cross 1, and this is 1 cross C, right? This is the overall things. Now let us see little more detail. See, this O minus T is very clear. This is anyway 2 C cross 1's difference. So it's C cross 1. This F dash into O cross C. See, this is a multiplying a diagonal matrix with respect to O minus T. See, if I do this multiplication, what happens? Only F dash multiplies with, first the element of this multiplies with the first element. Second row, in second row only non-zero is this. This multiply with second row, and so on. Finally, I get a C cross 1 vector. This can also be written as F dash net, which is also a C cross 1 vector, dot star with O minus T, where F dash net is written as like this. See, you can see here, I have just picked the diagonal elements. Okay, and then doing the element-wise product multiplication with the vector. So instead of writing the matrix vector product here, since it is diagonal, we can also write as vector element-wise product. Okay, so please note wherever in the subsequent derivatives. So whenever I back propagate from through the activation function, okay, the dou O by dou net can either be written as F dash into O minus T, or a vector F dash, matrix F dash into O minus T, or vector F dash into element-wise product with O minus T. Okay, the corresponding error at this location. Here corresponding error is this. And this together is what? Is nothing but the back propagated error, that is dou O by, so dou net by dou L. See, please note that we can write, so dou L by dou O is delta O, and this is delta net. Okay, so we write usually with the delta net. So any back error with respect to the L is written as L is the final loss here. So dou L by dou O here is written as delta O. Okay, similarly, I write here. So we can write here dou L by dou net. Net value that is there here before going to the activation is delta net. Okay, so we can write like this. So now let us write this as delta net. Delta net. So this essentially this can be written as delta net. Which is C cross 1, right? So now what is essentially now if we compute the whole thing together, bringing this and this together. So as we can see here, so what it happens is we are picking, let us put these two together. So what are we doing now? We are trying to pick the jth element in this row, okay, in this vector. So if it is C cross 1 here and this is 1 cross C, what I'm doing, I'm picking the jth element and multiplying with xi. So essentially what I'm doing, net j. So in delta net, we are trying to pick. So please see here, in this is delta net. Okay, in this delta net, I am trying to pick jth element. So it is delta net in delta net j, jth element of delta z, delta net, and multiplied by xi. That's what I have is delta y jy, delta w ji. Okay. So if bringing all this together, dou L by dou Wj, which is equal to delta j equal to dou del net j. No, that is the whole thing, del net j, bringing this here into xi, right? When we see for the whole matrix, what will happen? This will Wji, when we write for the whole matrix, this becomes a C cross D matrix because this is D cross 1 vector and this is C cross 1 vector. So we write in matrix form conveniently as to get this in element wise, we can write delta W as delta net into X transpose, where it is, okay, we are picking the jth row and the ith column, say, or jth column and ith row. Okay, that's what is happening here. Okay, in this jth column and ith row, right? Wj we are putting here, right? So this is what in matrix form. This is how we write the in vector formulation, the derivatives. So what essentially, what is the difference between this and this? Here we are mainly writing from the derivative with respect to the L and clearly indicating that backpropagating, okay, with element wise vector derivatives. Okay, vector derivatives are derivatives with respect to corresponding terms, right? So just to summarize, we will write it here. And in the next class, we will see with the computational graphs how this can be simplified much further. We will also see in deep neural networks where we have one or more or even several hidden layers, how to conveniently write this. So let me use different chunk here. So now here delta O is nothing but what? O minus T. Because as we have here, so in the forward pass, L is equal to O minus T norm square, right? You have here. While writing the derivatives now, please check, please just see the numerator, that's all. So just see what we have here on the top, that's all. Okay, so now O minus T. Here what happens? We will write, say, assume that, just interpret this as coming in forward direction, we are moving, we are taking the activation function F on net. So in the reverse, when we write delta net, what we are supposed to do is, so, or when we write, del dou net by dou O. So let us write dou net by dou O, that's nothing but F dash. Let us go step by step here. So dou L by dou O let us try to correlate with what you have previously done there. Dou O by dou net here is nothing but f dash. Please note that this f dash is a vector. Okay, I have written, though it's a matrix of say diagonal matrix, I have written conveniently as a vector, as we know that. So when we want to do back propagation, also to get the delta net, okay, so that is dou L by dou net if I want to get. So what I do is f dash star O minus t. Okay, so if I use the vector, what I will be doing is a element wise multiplication with this, right? Otherwise, if I have a matrix, I do direct multiplication, as we discussed before, right? Hope you are clear on this. So now, if I want to write the here, we are not interested here, but subsequently we may be interested. Dou L we'll see this. So here at subsequently dou L by dou X also we may be interested to write. Okay, we'll see that how to write. So before that, delta W, that is if you want to write dou L by dou W, if I want to write dou WJI. So what we have seen, f dash, this delta net. So this whatever you have here is delta net, right? So let us write directly in terms of delta net and delta net J into Xi. This we have seen in the previous derivative. So this comes from, because actually if you find the derivative, so net value equal to W into X, when you find dou net by dou Wij, you get actually the corresponding Xi into one hot vector, right? So that one hot vector we absorbed in net, and hence we got the corresponding element of net, that is net J, right? So this is what. So you can interpret now as any, so if you want to update W, if this is Wji, okay, if you want to update the weight, delta Wji, if you want to write, so what essentially we are doing is, so let us try to write for some other, okay, so if I am writing for this, okay, so if this is J and this is I, okay, so Xi related to OZ, then delta Wji needs, this is Wji, delta Wji needs the input from corresponding input here multiplied with the error here, delta net J. Okay, so you have here, whatever you have here, delta net J is from here, delta net J multiplied with Xi will give me corresponding update for the corresponding weight element, right? This is how it happens even in a bigger network, that we will see little later. For now, if you understand how to write the differentiations with respect to different vectors to vectors and vectors to matrix elements and elements to matrix or function of matrices to matrix, it is good enough. And writing the derivative for the loss function involves the back propagation starting from dou L by dou O to writing in in this order the derivative, that is back propagating the errors and multiplying with corresponding dimensions. Okay, so these things, when we especially take care, can be simplified as element wise multiplications as well. Okay, so this here we will stop in this class. Thank you.